Let's talk about what determines spontaneity. Which thermodynamic quantities? So the second law of thermodynamics said that for any spontaneous process, the entropy of the universe increases. So according to the second law, for a spontaneous process, this is the condition which must be met. Now, we don't often for a process actually calculate the change in entropy of the universe, so that's not always the most useful way to think about whether or not a process would be spontaneous, although that is really the definition. Now, we can look at this and say that the entropy change of the universe is determined by the entropy change of the system and the entropy change of the surroundings. We know that it's possible for delta S of the system to be less than 0 and for the process to still be spontaneous. And a couple of examples of that would be when water freezes or when water vapor condenses. In both of those cases, the entropy of the system goes down, but they are still spontaneous processes. So, for that to be the case, then delta S of the surroundings has to be positive, and it also has to be greater sort of in magnitude than delta S of the system. Okay, so this has to be positive. So let's think about then why that would be, right? So let's return to our examples. We had either water freezing or water vapor condensing. So both of these examples are exothermic processes. They give off heat as they happen. So these are exothermic processes. They give off heat, and that heat goes to the surroundings. And when that happens, this increases the temperature of the surroundings. And because we are transferring this energy into the surroundings are becoming more disordered, we also are increasing the entropy of the surroundings. Okay, so ice freeze spontaneously at low temperatures, but not at high temperatures. According to our argument, we don't yet know the answer to that, right? So one of the things, though, that we find is that delta S of the surroundings depends on temperature. So the enthalpy change of freezing is temperature dependent, but not strongly so. So we have sort of a fixed quantity of energy that's being transferred, and it turns out that the lower the temperature of the surroundings, the greater the change in entropy. So the lower the T of the surroundings, the bigger the delta S. And we can think about this, we have sort of a fixed quantity of energy that we're transferring. If the temperature is low, that energy goes a long way in changing the temperature, whereas if the surroundings are already at a high temperature and you transfer in a fixed amount of energy, it doesn't really go very far. So at low temperatures, delta S of the surroundings is actually bigger than at high temperatures. essentially saying the same thing again, but this explains why ice will freeze spontaneously at low temps, but not at high temperatures. And same thing with water vapor condensing. That only happens at lower temperatures. So we can then find sort of an expression for the entropy change of the surroundings. And so we know the following. We know that the entropy change of the surroundings is proportional to how much heat is transferred out of the system. And I put this negative sign here because this is the heat going out of the system. Okay? We also know that the entropy change of the surroundings is inversely proportional to temperature. It goes up more when the temperature is lower. So we can combine these two to get this expression for the entropy change of the surroundings. This is true for constant temperature. And if we further assume that we have constant pressure, then we can write that the entropy change of the surroundings is negative delta H of the system divided by T. Okay, so we're going to use this equation here, and we are going to combine it with this equation here. Delta S of the universe is delta S of the system plus delta S of the surroundings. Okay, so we're going to plug this in down here. And we end up with the following, that delta S of the universe is delta S of the system minus delta H of the system divided by T. If we multiply through by negative T, we end up with negative T delta S of the universe is delta H of the system minus T delta S of the system. And essentially, by definition, this stuff over here is equal to delta G for the system. So the change in Gibbs free energy of the system is defined by what's over here on the right side. So we can simplify this all now to say that delta G of the system is equal to negative T delta S of the universe. So if we come back to the question that I asked at the very beginning that said which thermodynamic quantity tells us about the spontaneity of the system, we can say that it's actually one of two, right? So either delta S of the universe has to be positive, according to the second law of thermodynamics. But if delta S of the universe here is positive, and this is positive, then this whole side is negative. So we can also say that another condition for spontaneity is that delta G of the system is negative. And either of these statements down here is a valid way to sort of define how a spontaneous process, if a process is spontaneous. This one is sort of the official second law statement, but like I said at the beginning, it's not always obvious to sort of calculate delta S for the universe, and instead what we often know is delta G of the system, and so this definition here turns out to be somewhat more useful to us.